multiple letters, I have two kinds of input, one is secret, one is public. Now to produce two kinds of output, which is secret and public. This doesn't cover you writing to memory, right? So your initial configuration of memory can be the input, the final memory can be the output. Whatever the attacker can see of the memory state will be your public output. This can work for your websites, where the input can be what's already embedded in the program. It can also be users' input as they interact with the program. For output, it can be the network calls to third-party, or you can, depending on what kind of secret you think about, right? You can think of third-party output definitely is public output. If you're protecting user data, sometimes first-party, sending data to first-party website can also be considered not so good either, right? You can do it a little differently. So if I think of system this way, I'm doing computation, I might take some secret data and then produce secret output. I could also take secret input somehow, get into parts of the public output. Some of the examples we showed kind of sort of similar, and then same with public input, and mix them, put them into different channels. So now, in general, information flow security trying to prevent or identify bad flows. Right? So in this specific example, flowing from secret to public is bad. Any other flow is fine. We're not leaking secret. This is a bad flow. Right? So a lot of information flow security is trying to do test system, runtime monitoring, or program rewriting to make sure this actually happens. Yeah.
If public input affects secret output, would that be bad for integrity?
If you do integrity, I'm going to change the label.
Oh, okay.
Right. I'm going to change this to be untrusted, trusted.
Oh, okay.
Yeah. So one input has aspects, right? So you can give it a secrecy aspect and integrity aspect, but both are important. And sometimes we don't care about secrecy, like set channel. We don't care about integrity. Other times we care about integrity and inclusion. Okay, so so now I'm giving one definition of non-interference, again by pictures. We'll do more rigorous definition when we have a language later on. So I have my system. So this non-interference, we're trying to figure out what do you mean by the secret. Again, we're staying the secrecy side for now. Just easier to think of various kinds of things. Think about I have secret in my system. How do I say that my secret somehow does not influence the attacker's observation? Right. So this is one way to do this. Is actually quite smart. I didn't come up with this, but it's both intuitive, it's kind of brilliant. So here, let's say that, let's make it a little more concrete. I have two variables, x and y. X is public, color green, or y is secret. So I have this program, it's actually bad. Obviously, the secret got out to the attacker. Right? We'll assume the attacker can see public variables, but not the secret variable. So the non-difference is defined as, if I look at two runs of this program, so here on top I have the first run, it take, let's say the y, red one is y, this y value is v1, and then x value is u. This produces me some output. So there's two output, one is public, one is secret. Color the secret one red, the public one green. Then I have another run. In this run, I force x to be the same. I force the public input to be the same, but secret is different. Now I run program with different secret inputs. Now this output, again I have two outputs. One secret, one is public. The attacker's observation are these two green output of these two runs. So non-difference is saying that it doesn't matter how I vary the secret input. In the end, the public output should be the same, because that's what the attacker sees, right? Like if you look back of the program we saw earlier, if the attacker actually, by running the program with different secret values, they see observation, then they can go backward to deduce what is the secret. Right? So the non-difference is saying that it doesn't matter what the secret is, the output is always going to be the same, because that's the only thing the attacker saw. Right? The attacker saw at the end of the program execution. So now this is a property defined by multiple traces, or using two traces to contrast the secret, the difference in secret. There are different ways of defining non-interference. In the PL, in the program language side, this is one of the very common ways to define non-interference. So here, if you look at this first program, right, so if I give y two different values, the observation x will be different, right? It violates non-difference. This is a bad program. This program gives information, right? All right, any questions before I move on? Anything else? I have another example. So this example, I first give y to x, then I clear it out. Is this program okay? Yeah. So it also depends, right? So it's okay because we're assuming the attacker cannot peek in the middle of the execution. If I allow the attacker to see at the end of the public, at the end of every instruction, I allow the attacker to see public memory, transiently the attacker might see y. But here we're assuming the attacker can only see the end memory, therefore the program is fine. Even though I temporarily give the secret to x, I clear it out, that's fine. I'm stripping out the secret before I finish the program. All right, so what about this one? This is like the branching, well, spectrum. This is not so good, right? I don't know why, but I know something about y. By me looking at x, I know y is greater than 0 or not. But by me varying this value, if I only vary with two different positive integers, the attacker won't see a difference. If I vary y with two negative integers, attacker also won't see a difference. But if the first value of y is greater than 0, the second value of y is less than 0, now the attacker sees a difference. Right? So this program violates non-difference, but doesn't seem to be as bad as the first program, right? Because I didn't need that much. So this non-difference doesn't capture how bad the program is in some sense, but does catch bad programs. So, and also in information flow term, this is called a explicit leak, because you directly assign secret to a variable. This is called an implicit leak because you cause a different in observation by control flow. So these are two terms that we use quite often. Any question about this? So next thing I want to actually go back to the examples. I want to go back to our example to actually now think in terms of non-difference, to both in terms of do they violate non-difference, right? So, and also can we use the newly learned URLP or the lattice model or the final security model to rule out these programs? So let's go back to the example. I think actually on the screen. So these examples are similar to the one I showed in the previous slides, right? So I have some directly sending, the attacker's observation here would be on the internet seeing what's being sent, right? If you give a different password, the attacker will see a different observation, right? The non-difference is violated, it's a bad program, right? So in terms of fixing this, if we're still in the land of DWL, we think that runtime is going to catch this. How do I catch this? Any other people who in the back? Any thoughts? So in DWL, we're labeling stuff. How would I label stuff? So this first program will be ruled out runtime. You can type this one, or you can type yet.
Label password as secure, label send as unsecured, so you can't combine them.
Yeah, almost right. So password is secret. Send argument is supposed to be low or public. But when you do this call, I can runtime match the argument type with the argument type with the real parameter type, or the other way around. If they don't follow the lattice, I'm going to reject this program. So the next program, same thing, right? If I vary password, if you are the attacker observing on the network, you actually see a difference, right? The report will be different depending on which password you take. So here, when I do label, so password will be secret and label, report should be labeled low. This sending is actually fine if I send individually, because send is low, report is low, send itself require low argument, this is fine. But this assignment is a problem, right? I'm assigning a secret to a low variable, so I should stop it at runtime, or if you manage a type system, I can rule this out statically, because this is explicitly. So what about this one? This looping thing. Because I want to mark output as low. Yeah, I'm gonna mark output at low. Partial length you can do. Yeah, you can figure out what's the partial length and then how do we actually get this program. If I mark output low, this setting is fine, right? Because I'm setting a low thing. How do I rule out this? Hey, I don't have a thought. Yeah.
Can we mark the operation of reading out of a secure thing as also secure? And sort of like track the typing to say, okay, C now is also a secure thing. And if we're adding, oh no.
Yeah, I'm adding constant.
Yeah.
Constant is low, right? Constant has no secret. What's the problem? Yeah.
So I guess if you're accessing a property from password, and then you also have conditionals pass the, I guess the label to,
Yeah.
Yeah.
Yes, you're exactly right. So this branch, this if branching, is depending on secret, right? If you branch on secret, you have implicit leak, right? So then this assignment becomes bad. Somehow, either monitoring or type system, you have to understand that this assignment to this low variable is done under a branch depending on secret, right? This kind of assignment is bad because if this C is not secret, it's fine. But now this conditional is depending on secret, I should rule this out. Yes, it's doable, right? So we'll see how we do that tomorrow, both with type system and runtime monitoring maybe in the third day. Yeah.
So just, at the point, if we're doing forward analysis and we're looking at output,
Yeah.
we don't necessarily know where output is going,
Yes.
right? So the operation isn't necessarily improper. We just would then say output is secure.
So you have a point in that depending on how you think of how do we do this, right? Even in type system, in the easy way, I'm going to label all my data ahead of time. I'm going to say output is low, length can be low or high. You can give it high, and then send require a low input. So I'm going to fix these labels, and then I'll do my checking. You can also do a different way where maybe you think about random typing or thinking at runtime. But I don't know what output is, but I want to give a label as I go along. Right? Initially, output is unknown, or maybe you can say initially it's low. But as I'm doing assignment inside the high branch, I'm going to say, oh, actually now I realize output is depending on secret. I'm going to change label to high. And now when you get to output, I'm rule out the program here. That's how we do this. Yeah.
Is the for loop itself a problem? Because how many times you execute the loop body depends on high information.
Yeah.
Right?
Yes. So the stopping early part would be that problem. This is a specific program. You can also think, oh, length doesn't matter because the problem is on length.
So just to make sure I understand, so any kind of encryption will be ruled out from your system? Any kind of encryption will be ruled out by this kind of reason, right?
So you can hide the information. So you can hide this information by, let's see.
Because you never talked about how similar, how you can deduce the secret from this effect on the output. We have
Yeah, that's a slightly different. Yeah, encryption is something else. Encryption is almost like declassification if you don't have a key. Now, if we're talking about attacker program, the attacker try to think about you have a network scanner, try to figure out whether you're actually using 0 or not. You can take a encryption, or just to generally encode you can encode this with something else. Then my network scanner will now see your leaking password. But in terms of non-interference, depending on secret, the output are different. Right? So the program is bad. Now, if I'm actually doing encryption for good, if I want to hide secret by encrypting using a key only me and the other person knows, the attacker doesn't have the key, therefore this is okay. that's a different property, because we have to assume encryption being a classification operation, because you have proven that this encryption is some, I don't know, as DCPA secure or whatever. Therefore, without the key, with very low probability, the attacker will be able to reverse the context. That's a slightly different property. We'll talk about division next.
I guess we have to leak some information, right?
Yes, we have to do some information. When it's a password check, which password checker doesn't tell you it's right or wrong? Right? You have to tell people something. Yeah. Yeah, exactly. So yeah, that's how we'll talk about this.
So I mean, we need some quantitative analysis, right? And how much information we reach.
Yes, yes. So quantitative information flow is one field, except that I'm not going to cover it in this lecture. But yes, the current work in that space as well. All right, other questions? Yeah.
It seems like you are giving a system on
We
this.
can. Yes.
So, you know, the partial RNA system. Question is, what happens with recursive call for invested, you know, 6.9%
Yeah. So the same with every recursive function, you assign a type, right? So here we assign a label. In here, we actually have finite labels. So you just assign a label, you check that the body also performs, also function label. So we don't have, so very few type systems will actually do the changing label. Most of them decided that you have to mark everything to the proper label, and we'll check it.
Question. Sometimes I can do this by channel classes to constant computation, and I was wondering if that would apply here to the code. If there was a maximum length on the password, and we knew that length in advance and it was always the same, let's say 16, could we incorporate that into the loop somehow to not violate the non-influence?
So,
In the event that it fails, it's the right length. Or
so if you have fixed length, then length information is public now, right? It's not a secret in some sense.
I think the question I would say is whether they enter the password at the correct length or whether they enter the password at the wrong length, the loop still iterates for a fixed
Oh,
number of times.
yeah.
Would that fix one of the non-interference problems?
So this one no, right? So this one is actually let's see. I think we have one example. Let's see. This one. This one is a bad example to begin with, right? So timing is an issue. Again, if you think about how this is a problem. Yeah. So if timing is an observation, then it becomes a problem, right? So far we have not said timing being observation. We only say, oh, the ending, the input output, the ending memory is your observation. Now this program, the bad thing is that if your password is incorrect, the timing is different from if your character is correct, right? So there's a diff in observation and timing, right? So to mark this as being insecure, we have to change our formulation of what the attacker can observe. Once we add timing being an observation to make it more secure, now you can do this, right? You can have the time change. You can either you don't stop when it runs wrong, right? You do the whole check, right? And if your entire length is a secret, then you pad it up so that the attacker cannot see that. Yeah, so that's this example. Okay, this is since I'm here. Yeah, any question about this example? How do we actually get this done? In terms of how do we mark this as being bad? I can just, yeah.
We make the duration part of the input.
Yes, yeah. So yeah, but with the modeling, right? So when you model the system, every step, you also output the time of one step. I think we'll stop here. So we can come back. I think now we'll do tomorrow. Try to better. All right. Yeah, I'll stick around. If you have questions, you can ask me tomorrow. We'll do more.